Hi, Professor. My name is Shuo Zhang, and this is my presentation of my final project of CISC614. My research is about the application of machine learning methods in rainfall and runoff modeling. In my research, different modeling methods will be presented through a case study of CISC River drainage area in New Jersey, and the performance of different models will be evaluated and discussed. It is expected that the application of machine learning methods will provide an accuracy and reliable runoff model in this research. As a practitioner in water management and stormwater management, a good runoff model provides important information for water infrastructure design and optimization in my work. So the most common model I'm using is the prediction runoff model system, which is website and physical process-based modeling system. So I'm interested in the story behind the system and the other modeling methods with the knowledge I'm obtained from computer simulation course. So this is the motivation of my research. So first, let me introduce the hydrology modeling of water cycle. The water cycle describes the transportation of water in the natural world. As shown in this figure, the water cycle includes several phenomena such as rainfall, evaporation, transpiration, infiltration, surface runoff, and groundwater exchange. The rainfall runoff model is a mathematical method used to describe the relation between rainfall and runoff. And the modeling can be categorized in empirical, conceptual, and physical model. The empirical model is the historical data-driven model, which was used input data as training data, and through a black box procedure, the model will be used to predict future surface runoff. And the advantage of empirical model is fast and reliable, but it fails to consider the effect of environmental change or the severe weather conditions. And the conceptual model uses simplified equation represents the water storage of catchment, and they use the historical data for calibration. But the spatial variance was raised in this method, and the model is area specified and not universal for the other study areas. For the physical model was the physical laws based on the processing water cycle take into consideration. It eliminates the spatial variance, but is very cost-consuming in time and computational ability. So in my research, I was trying to combine a different model with limited data and apply the hybrid machine learning model to improve the performance of the prediction. So the basic model is based on this water balance, where P is the precipitation from a rainfall event, QS is surface runoff, ET is the evapotranspiration, and SM is the change in soil moisture, and the GW is the change in groundwater storage. And there are 4 input variables in this model. I was trying to eliminate some inputs by established an interrelationship of each input variable with precipitation. Then predict the surface runoff by only input variables, which is the precipitation. So before building the submodel, there are some assumptions need to make. The first is the rainfall event happens uniformly, and rainfall intensity and duration was not considered. And the second is all the water from rainfall drops on the drainage surface, and the factors such as urbanization and green infrastructure, which will affect the infiltration, will not consider. And the third is the effect of evapotranspiration was considered as an average performance in the state. Vegetation and soil type were not considered. And for the groundwater, the storage level was considered as uniform. And when the submodel is defined, the final model can be determined, and it showed a second-degree polynomial relationship in this case. So that is how I combine a physical and empirical model for this case study. And the submodel different from the basic model of the evapotranspiration versus precipitation, and the groundwater levels versus precipitation model. And it's supposed to have another model, which is the soil moisture in this equation. But I was not able to find enough soil moisture content data for this case. So I just ignored the effect of soil moisture in this model and consider it as a constant. So then I applied the machine learning techniques, which are the multi-layer neural network, support vector machine, and gradient boosting regression. And a hybrid machine learning model is constructed to combine the performance of different single machine learning model. I also created an empirical model for comparison, which is use the artificial neural network with historical precipitation and the runoff relations to predict the future runoff. And so here is the result of this case. So the result was not shown as expected because the R-squared score for all the model are less than 0, which means it makes no sense to use nonlinear regression in this case. But when I reviewed the prior research by the other researchers, it shows that the rainfall runoff model is a complex model with high nonlinearity. So what I'm thinking is the problem is maybe in the data gathering process. The variable I selected for the runoff modeling is not proper. In some article, they use the rainfall intensity and the duration data to describe the rainfall event. But in this case, I'm using the monthly average precipitation instead. And for the evapotranspiration submodel, and some physical-based model use the evapotranspiration equation to calculate the amount of evapotranspiration. But in this case, I just build a submodel of the relationship of between evapotranspiration and precipitation, which is not accuracy enough compared with applying the physical laws. And for the machine learning model building, it improved the performance compared with the basic model, but the limitation of the data makes the prediction not perform as well as expected. I think more data will be helpful and more features should be introduced in the machine learning model if possible. So let's go to the code presentation. So here is the water balance equation for constructing the basic model, and the water gains from the surface runoff is the water gain from the precipitation minus the water loss due to the evapotranspiration and minus the water loss due to the soil infiltration and minus the water loss in groundwater storage. So the precipitation data I used in this project is the New Jersey statewide monthly total precipitation, and this is the data source. And next is for the unit conversion for the input data. And for the other variables, evapotranspiration, I gathered the monthly average potential evapotranspiration from this data set. And then for the change in soil moisture, the soil moisture data was not able to find from the open resource, so I just assumed that the amount of the water loss due to absorbed by the soil is constant. Next is the change in groundwater storage, and the data is gathered as a monthly average water level below the surface. This is where the data come from. And for the current model, the target variable is surface runoff, and the 4 features variables are the water gain from precipitation, water loss from evapotranspiration, absorption of soil and infiltration to groundwater. So I'm building a connection of evapotranspiration with precipitation and the groundwater with precipitation as submodel. And for the other variables, we consider it as constant. So I input data, and the first submodel is the evapotranspiration versus prediction. So just from the plot, I'm going to assume the relation of these two components is a second-degree polynomial relationship. So then I applied the least square criterion for determining the coefficient of this polynomial equation. And this is the first submodel. And for the second submodel, which is the precipitation versus groundwater level, we just do the same thing as before. and assume a second degree polynomial equation and determine the coefficient of this equation by d-squared criterion and got the second submodel, and then combine the two submodel with the precipitation model, and we can have the final model of this empirical model. And this figure shows the prediction value versus the actual value. Then for the performance evaluation, I use the mean absolute error, mean squared error, and R-squared score from the scikit-learn library. And the performance will be discussed later. The R-squared score in this case is less than 0, which means this model makes no sense in run of prediction with the given data. The model needs more data for calibration, or more water circle process would be introduced in this model. And then apply the machine learning method for prediction with limited data and input variables. So the three single machine learning model I applied is the multi-layer neural network, gradient boosting regression, and the support vector machine. So here is the here I input the raw data, and this data set includes 120 sets of data from 2010 to 2019 with the features in 6 columns. And then I applied the exploratory data analysis. And so this figure shows the data correlation of each features. So then I split the target variable and features, and then I apply the data preprocessing for this data. So for this data, missing value is not detected, and there is no categorical variables in this data set. So we don't need to deal with the missing value by filling and convert the categorical to numerical variables. So the only thing we need to do in the data preprocessing is to scaling the data set, because they are coming to different units. And then then is the train test data split. So in this case, the train size of the data is 80%, which means 80% of the data will goes into training the model, and the rest of 20% will for evaluation testing. And then I use the multi-layer regressor in scikit-learn library, and gradient boosting regressor, and support vector machine. So in this case, the kernel I used for support vector machine is polynomial, and the degree is 2. And this is for the single machine learning training and testing. So for the hybrid machine learning model, I just build a pipeline which include data preprocessor step to scaling the data, and then the bench model models goes into the hybrid model is the 3 single machine learning model I just applied before. And for the hybrid model construction, I used the stacking regressor in scikit-learn library and use the linear regression as the final estimator. So the final estimator in the hybrid modeling is the way how the performance of the single model combined together. So here is the construction of the hybrid machine learning model pipeline. And then this is for the model training and testing. And then for the empirical model, I just applied 2018 as the historical data to training the empirical model and use the 2019 data for the prediction and testing. So here is the result. So as I mentioned before, the result is not as expected because the data gathering process is not as expected. It is better to use unit hydrograph data instead of drainage discharge to reflect the surface runoff. And I'm unable to find enough proper data for the study area. And in conceptual model, which is the machine learning modeling, the potential features may affect the surface runoff is not considered enoughly, and the features just based on the variable used in physical modeling. And the rainfall runoff model is a complex model, which means the single physical equation cannot provide enough information for well prediction. And so this experience is impressed for digging into more about the rainfall runoff modeling. And even though the result is not as expected, I'm gonna keep my research with more data and consideration about the proper input variables, and will focus more on the physical laws to construct the submodel. And this is pretty much about my final research. Thanks for review.